My dear student, colleagues, and all the viewers who are watching this program live from Facebook page Physics Adda and School of Astrophysics and Astronomy and YouTube channel Pretam Kumar Das, I'd like to welcome you all to our International Physics webinar. So, good evening to all here in Bangladesh and a very good morning to all those who are watching this program live from USA. So, hope you are well and safe from Corona pandemic. So the recently the COVID become very worse, so we have to maintain our health rules. So today it's our 152nd International Physics webinar. So all we know that we cannot continue our normal academic program inside the campus due to the COVID since March 2020. The as we cannot continue our normal academic program, so we have to start our online program. I think you have already come to know that the Department of Physics, Pabna University of Science and Technology has started its online program, including online international physics webinar. We have successfully completed our 151st international physics webinar. Today it's our 152nd international physics webinar. Today it's very important day for our department. Today I'd like to welcome you all through a joint session between the Department of Physics, Pabna University of Science and Technology, and the Department of Physics and Astronomy, Louisiana State University, Louisiana, USA. So we have with us here today Dr. Gabriela González, Madam, LSU Boyd Professor, Department of Physics and Astronomy, Louisiana State University, Louisiana, and she has already connected with us. So I'd like to welcome our speaker. Madam, good morning and good evening here. So thanks for accepting our invitation, Madam. Would like to
Yeah,
say thank, yeah, on the behalf of the Department of Physics, Pabna University of Science and Technology for accepting our invitation. So I'll take a few minutes to introduce you with my student and then you can start your session. So for those who are new, I'd like to inform you all that we have divided our webinar into three parts. First of all, we'd like to introduce our speaker with all of you, and then our speaker will deliver her speech, and at the end we have a discussion session. In that time anybody can join with us. You can also ask question by commenting. And I think you have already come to know the title of this today's international physics webinar. The title is very interesting and exciting, Gravitational Wave Astronomy, and our speaker is Dr. Gabriela González, LSU Boyd Professor, Department of Physics and Astronomy, Louisiana State University, Louisiana, USA. And we can see his educational and professional background. Gonzalez received a degree in physics at the University of Cordoba, then attended Syracuse University, where she earned her PhD, joining LSU in 2001. Gonzalez, who is in a tenured professor in the Department of Physics and Astronomy, is a member of the National Academy of Sciences, a fellow in the American Academy of Arts and Sciences, and was recently named the 2019 SEC Professor of the Year. She is the best known for her work with the LIGO, the research collaboration that produced the direct observation of the gravitational waves, resulting in the 2017 Nobel Prize in Physics. She has been continuously funded by the National Science Foundation for her work on instrument development and data analysis in the field of gravitational wave research. For more, you can visit this link. Professor González research interest in the detection of gravitational waves with interferometric detectors, such as one of the in the LIGO Livingstone Observatory in the Livingstone, LA. She has published several papers on the specific publication of Brownian motion as a limiting sources to the detector's sensitivity. She was a founding member of the LIGO scientific collaboration and has participated intensely in the commissioning of the LIGO detector at the Livingstone Observatory since joining LSU in 2001 in issues related to the alignment, sensing, and control. Our group is very involved in the instrumental characterization and calibration of the data collected in the data taking science runs performed by the LIGO scientific collaboration. From 2000 to 2007, she co-led one of the 4 data analysis group in the collaboration dedicated to the search of the gravitational waves generated by the binary system of the compact object, neutron stars or black holes, in the final in spiralizing stage before correlations. In 2008 to 2011, she led the LSC detector characterization working group. In 2011, she was elected as the LSC spokesperson. And you can see her Google Scholar ID, and her citation number is 61,220. So this is a recent publication. So thanks for all of your patience. Now it's time to go to our speakers. Madam, thanks again for accepting our invitation. It's your time, madam. You can start your session.
Thank you for the invitation. It's very nice to be here, even though we are across the world.
Yeah.
Sharing.
Due to the corona pandemic. Otherwise, we can arrange a face-to-face session. And hopefully after the COVID.
Okay. Okay, so again, thank you for the invitation. And I want to tell you about a new field, a field in which many of us have been working for decades, but it's a new field because it's only 6 years ago, less than 6 years ago, when we made the first discovery of gravitational waves. So we call September 14, 2015, the birth of gravitational wave astronomy. But let me start at the beginning, and that is with Einstein's theory. Einstein's theory of general relativity. You might have seen this formula before. The theory is based on what seems a simple equation where we have the Einstein tensor on the left that is constructed from multiplying derivatives of the space-time metric. This is a metric, this is the main object that tells us how to measure distances and times. And that metric through this equation is determined by this stress energy tensor that tells us where the matter is, where the energy is, and how it is moving. So the matter curves the space-time, and the space-time makes the matter move. That's what this equation is telling us. And it's a theory of gravity, so it has Newton's constant, and it's a relativistic theory, so it has the speed of light in here. As in Maxwell's equations, if we set the matter source is equal to 0, we have not exactly a wave equation like in Maxwell's theory, but we have an approximate wave equation if we assume that the space-time metric is just the flat space-time metric, what we call Minkowski metric, plus a small perturbation. You might remember that in the appropriate units, Minkowski metric is -1, 1, 1, 1, a diagonal metric, so it is dimensionless. So this perturbation is actually interpreted as a change in length divided by length. And like I said, if you set T mu nu equals 0, then this equation becomes a wave equation, first order in this h mu nu. So the solution is a quadrupolar wave, a transverse quadrupolar wave. So if this is the direction of travel, then we define distances, defining a circle. All the distances to the center are the same, but if there is a gravitational wave traveling in this direction, those distances will be changed. First, stretching the circle in one direction, then a circle again, and then stretching it in an ellipse in the opposite direction. This is one of the polarizations that we call the plus polarization. This is the cross polarization. So there are two polarizations of this transverse gravitational wave. And because of these distortions of distances, one thinks that measuring it with an interferometer that measures changes in distances, differences in distances between two arms would be the best way to do it. And it is, except that this magnitude of h is predicted to be very, very small. And that prediction comes from the formula that relates the sources. These are masses that have a quadrupole moment, so they are not perfectly spherical. And that mass quadrupole is changing in time. And then through this equation, that change in time is what produces this gravitational wave. However, you can see again Newton's constant, c to the fourth. This is the distance to the source. So when you put these numbers together, and this is what Einstein did in 1916, less than a year after publishing the general theory of relativity, the numbers were so small. For example, you might have heard that we know of gravitational waves. Not that long ago, there was a long discussion on whether gravitational waves existed or not, or whether they were a mathematical artifact. But in the 70s, there was a binary pulsar discovered, a system of two neutron stars that are orbiting around each other, in fact, orbiting around the center of mass. We call that a binary pulsar. This was the first binary pulsar discovered by Hulse and Taylor in 72. And what they saw is that this orbiting emits gravitational waves. They didn't see the gravitational waves, but those gravitational waves are carrying away energy, which means that the stars are getting closer and closer. And they saw that change by measuring it over years, over decades. They saw the neutron stars getting closer and closer. The prediction is that the gravitational wave emitted by this system, or by any system, any binary system, will be like a sine wave related to the orbital frequency. But then as the stars get closer together, they are orbiting faster, so the amplitude increases because this second derivative brings an omega squared here. So the amplitude and the frequency increase until the two stars merge in a single object. So this is what's expected. The signal is largest at the coalescence, but for this particular pulsar, that will happen in 300 million years, so we will not wait for this pulsar to happen. And in fact, we probably won't expect one to happen in our galaxy, because that happens once every 10,000 years or so. So we have to look a bit farther. If we look for binary pulsars in the Virgo cluster that coalesce once every 50 years, then we might see an amplitude at the merger of 10 to the minus 21. 10 to the minus 21. That's a fractional distance. That is like comparing atomic distances to the distance between the Earth and the Sun. It's an almost incredible number to think that we can measure that with an interferometer. But we did. We did it on September 14, 2015, not from neutron stars, but from black holes, from merging black holes. They were 400 megaparsecs away, quite a bit farther away than the Virgo cluster. And the peak amplitude that we saw was 10 to the minus 21. Amazing. So let me go to the instruments. The instruments are Michelson interferometers, but they are big. They are big because what we are usually limited by is in measuring changes in distance. So this is very small, but if we multiply that by a longer distance, well, then we have a larger change in distance. So these interferometers, the ones in the US, excuse me, there are two in the US, one in Louisiana, Livingston, Louisiana, near Baton Rouge, where I live, another in Hanford, Washington, and they are 4 kilometers on the side. And not only that, but we make the light go back and forth several times, many times. These two interferometers took data together with the Virgo interferometer in Italy, which is managed by a European collaboration, the two LIGO detectors, and the GEO 600 detector, which is a 600-meter detector in Germany, are managed by the LIGO scientific collaboration, but we collaborate with this other collaboration, the Virgo collaboration. And now we're also beginning to collaborate with a collaboration based in Japan that manages the Kagra detector, just became operational very recently, and there's still another observatory being built in India. So this is a global network, and it will become clear why do we need a network. Now, these are not simple interferometers. We need to make the laser powerful and steady, And we actually are operating now the detectors that made the discovery were what we call second generation, where we installed a laser that was more powerful than in the first generation. That laser is provided by, the technology is provided by the Max Planck Institutes in Germany. And that laser travels in vacuum tubes 4 kilometers. So there are 4-kilometer vacuum tubes, which are not small. They are 1.2 meters in diameter. They are protected by a concrete enclosure. The mirrors at the end are not these tiny mirrors that we boil down to optical tables. They are big, 40-kilogram heavy masses. We use an infrared laser. So these are mirrors in the infrared. That's why they look reddish. And they are made of very pure fused silica, which with a very, very state-of-the-art polishing and dielectric coating for building the mirror properties. And that mirror, to make it look like a free mass, because the distances that we saw changing in principle are distances that change the distance between free masses. We have this mirror hanging from a quadruple pendulum. Of course, it's not a free mass. If not, it would fall to the floor, but it is approximately free in the horizontal direction. But that's not enough. We need to make that quadruple pendulum hang from a complicated active seismic isolation system. Here you can see the size, if you see people on the side. Here we measure the relative motion of the different layers, and we push to cancel that motion as transmitted to the suspension. And all of that is inside vacuum. So you need to hang it all together, to prepare it all together, and then close the vacuum. Of course, we have lots and lots of control systems to know where the mirrors are and push them as appropriately. And then you might see here, if this is a beam splitter, then this is a very short interferometer, not 4 kilometers long. But that's because what we have is a much more complicated system than just a simple Michelson. We make the light go back and forth between two mirrors, one mirror at the end of the 4-kilometer arc and another mirror here near the corner. So this is using a fabric Perot optical cavity. We keep the distance between the mirrors so that the light go back and forth with resonance, with constructive interference. And what that means is that the light coming back brings us information of a much, much longer trip than just 4 kilometers. We operate this so that the interference that happens at the output is destructive interference. We call this working on the dark port, which means that the interference going back to the laser is constructive. So we put another mirror in there to send that light back, to recycle that light. We call this the power recycling mirror. And that's not all. We have a signal recycling mirror. And then we have lots of other instrumental tricks that we do, including quantum optical techniques to manage to squeeze the vacuum at the end. And after all of that, we have photodiodes on which we measure noise. In general, what we measure is noise. And the question is, how big is that noise compared to that 10 to the minus 21 that we mentioned? And that depends on the frequency that we're talking about. So what we usually do is decompose the noise as a function of frequency. And this is what we predict the limiting sensitivity would be. This black line is what we want to achieve. We are not there yet. It takes several years to reduce the noise until we get there. But this is where we want to go. And you can see that this is smaller than 10 to the minus 21. It's 10 to the minus 22, 10 to the minus 23, but it depends on the frequency. This purple line is the quantum noise. It's the quantum noise that is short noise at high frequencies, radiation pressure at low frequencies. But if you do a properly quantum treatment, then this is the quantum noise. And it is on this side that we can use this vacuum squeezing that I was saying, and we have been using it in the last couple of years to reduce this side. We are also limited by Brownian motion. The masses are at room temperature, so they are vibrating. The atoms are vibrating. But the amplitude of that vibration, the amplitude of that Brownian motion at different frequencies depends on the sources of energy loss. This is called the fluctuation dissipation theorem. That's what I did my thesis on. And it turns out that at this point, we have reduced the Brownian motion of the fibers that hang them by using glass fibers, few silica fibers, the substrate. We are only limited by the Brownian motion on the coating of the mirrors. And that is this red line in here. But we also have lots of other noises. We have at lower frequencies, we especially have the seismic noise. The seismic noise and the suspension thermal noise are the ones that are filtered by the pendulum, so they decrease very quickly, but they dominate at low frequencies. So this is where we want to be, and when we get there, we like to translate this amplitude, this noise spectral, noise spectral density into a distance. How far can we see a coalescence of neutron stars? And with this, we could see a coalescence of neutron stars 170 megaparsecs away. A parsec is 3 light years. We can see black holes much, much farther away. So for a binary black hole system of 30 solar masses each, that's about what we saw for our first discovery, we could see them at 1.5 gigaparsecs, much, much farther. Black holes have larger mass, produce larger gravitational waves, so we can see them farther away. Remember this number because I will talk about the reach of the detectors in future slides. So I told you that on September 14, 2015, we saw this signal and this peak-to-peak amplitude. Well, this peak amplitude is 10 to the minus 21, 10 to the minus 21. And the two signals that you see in here, this was in the cover of Physical Review Letters where we published this result, those were the signals in the photodiodes at Livingston and Hanford. It looks like noise here, and at the end, that's what we always look, what the signal always looks like. But here there is this sine wave that increases in frequency and amplitude, and then it disappears into the noise. That's a merger. And from the frequency, we can tell the masses, the frequency and the evolution of the frequency, we can tell the masses of the black holes. And these black holes were 29 and 36 solar masses each. Nobody had seen black holes of that size. Stellar black holes, which are the ones that we expect that produced by supernova explosions, have been seen up to around 10 solar masses. Of course, there are million solar mass black holes and billion solar mass black holes at the center of galaxies because of all the accretion around them. But these are the original black holes after being born from supernova explosions. And these were bigger than anybody thought. From the amplitude, we could tell how far away these were, and these were 400 megaparsecs away. 400 megaparsecs away. That means that they took more than 1 billion years to get to Earth. We saw the past. We saw a signal that came of an event that happened when on the Earth, not only there weren't humans, there were only multicellular organisms getting organized. So while on Earth, there were fish, and then and then animals, and then people, and then scientists, and then Einstein, and then us building the detector. While all of that was happening, this gravitational wave was traveling to us. I had the honor to participate in the announcement of this discovery, which we did on February 11, 2016. And on stage, we were with Franz Cordova, the director of the National Science Foundation, which had funded this project in the US, Dave Wrightsey, who is the executive director. I was there as the leader, the scientific leader of the LIGO scientific collaboration, and Ray Wise and Kip Thorne were there. They were the two scientists at MIT, Ray Wise and Caltech Kip Thorne, that began proposing this project and promoting this project in the 70s. In the 70s, it was built. The LIGO detectors were built in the 90s. And it was only in 2015 that we got the first detection. So these projects take a lot of people, and not just a lot of people, but a lot of time. Notice that the article was signed by the LIGO Scientific Collaboration and the Virgo Collaboration, even though the Virgo detector was not yet operational at the time, but we had decided long ago that we were going to publish and do the analysis all together, regardless of which detectors made the discovery. And I was very happy we did that. This article had more than 1,000 authors. And not long after this, in 2017, there was the Nobel Prize, the Physics Nobel Prize announced, and it went to Kip Thorne, Ray Wise, and Barry Barish from Caltech, who had been an executive director of the LIGO laboratory at the time where things were not working very well. And he not only managed the project very well, but also had the idea to create this broader LIGO scientific collaboration. But notice that even though there are affiliations at MIT, academic affiliations at MIT and Caltech, in the Nobel press release, there was this recognition of teamwork because the affiliations were LIGO-Virgo collaborations. So this was Nobel Prize work. But we didn't do it for that. We did it to do astronomy. So let me tell you now about the astronomy we have been doing with the detections. There were more discoveries, not just that first one. People often ask me, so what's next? What's next? Well, we never wanted just one detection. We had no doubt that Einstein was right. What we wanted was to do discoveries so that we could do astronomy of black holes. Black holes do not emit light, so now we can see other signals from black holes, which are the gravitational waves. We took data, as I said, in 2015, 2016, 4 months. And this number, 80 megaparsecs, is remember that number that we construct from the nice curve? That's a sensitivity that we had in that first observing run. But remember, I told you that the hardware we installed could lead us to 170 megaparsecs, more than twice this. So we had decided long before this that we were not going to wait to be perfect. We were going to begin taking data as soon as we had significantly more sensitivity than in our previous generation. And we're very glad we did that, because that's when we saw this whopper signal. We took a break, and then we began taking data again in November of 2017 for about 9 months. And at the end of that, in August of 2017, this was November 2016, sorry. And in August of 2017, Virgo joined us again with less sensitivity. We had more sensitivity than we had in the beginning. In that first observing run, we not only had that first detection in September, we had another in October, another in December, all from binary black holes. And then in this second observing run, we had 7 more detections of binary black holes. The more sensitivity you have, the more distance you can reach, so the more signals you expect. But we also had a coalescence of neutron stars. And several of those binary black holes and this coalescence of neutron stars were done with 3 detectors, not just 2. This is a plot that I love. This is a plot that shows not just the waveform that we discovered, and you might see in here there is an orange waveform, which is the prediction, our best fit to the prediction, and then you see some gray shading. That gray shading is our reconstruction from the data without using models. But what I like the best is this plot that shows where the brightness shows the amplitude, and this is time, and these all black holes have the same time axis, half a second. Half a second, it's a very, very short signal, and this shows the frequency. So as the, and this of course is the first detection, as the signal gets higher frequency, this has what we call a chirp waveform. Chirp because of the sound, but when we look for this shape, we know that there is a gravitational wave in there. And you see that some are not as obvious as others. Of course, we don't look at this diagram. We actually do very heavy computational work to detect the signals, and we can measure the probability of this signal being due to the noise in a false alarm rate. And these are all the ones that can be clearly detected in the noise, even if they are barely visible in here. But this one, which was in August of 2017, is qualitatively different. This here, we have the time axis in tens of seconds. And you see that this is actually not as bright as the others, but it is much longer. So this one has a signal-to-noise ratio accumulated in this trace that is much larger of all these other signals. The amplitude is smaller. The amplitude record is still that of the first one, but this one, excuse me, has a much, much higher signal-to-noise ratio. Now, the difference, what makes a difference of these being short signals and these being long signals is the masses. The larger the mass, the lower the frequency at which, the lower the last frequency of the merger. And sometimes if the frequency is too small, then it's out of our sensitive band. Remember, at low frequencies, we were very, very, we have a noise dominated by seismic noise. But the smaller the stars, and neutron stars are about 1.4 solar masses each, the smaller the star, then the larger that frequency, and then the more time the signal spends in our band. That's why we can see this signal for so long, because it goes to higher frequencies with very, very high signal-to-noise ratio. So we could tell that these were small stars. Now, could we tell whether these were binary neutron stars or small black holes? We couldn't. But it turns out that, and I will show you later, not we in the LIGO collaboration, but in the world scientific community, they saw electromagnetic signals coming from the same location. So let me first get you some of the results that we got from this catalog. This is the first catalog that we published. And the first thing that we can do, and that many people expect us to do, is to test general relativity. And we do that with several different methods, and I can go into the details, but the bottom line is general relativity passes all our tests. So we have no evidence of deviations from general relativity. Now, there are a lot more sensitive tests than the ones we do, but the ones that we do are in a regime that's not achievable by any other method. So this is a qualitatively different test of GR, and GR passes the test too. Now, about localization, that's a bit of a story, because with 2 detectors, like when we had the first detection with the LIGO detectors, you cannot quite tell where the signal comes from. We had a 7 milliseconds difference. First it came to Livingston, and 7 milliseconds later, the same signal appeared in Hanford. So from that time difference, you can say the signal comes from a circle in the sky, a circle that's closer to Livingston than Hanford, because it came to Livingston first. But if you use some analysis of the phase differences and amplitude difference, you can say, well, this part of the ring is the one that has the most probable localization. But that's not a lot. See, we have these big bananas on the sky. That's not a good localization to tell astronomers. But if you have 3 detectors, and there are some of these that were detected by Hanford, Livingston, and Virgo, then you can localize it a lot better. That's a much, much better localization. And this one was that neutron star localization. That one also had the best signal to noise ratio, so it has the record of the one being the best localized. So here we could tell astronomers, go and look there. And they did. This is that localization on the sky. There was a gamma ray burst detected at the same time by Fermi, the Fermi satellite, and the localization of that gamma ray burst was consistent with the one from LIGO Virgo, and the difference was only a couple of seconds. The gamma ray burst came only a couple of seconds after the coalescence, the measured coalescence of the systems producing the gravitational wave. So there was already suspicion that these were neutron stars and not small black holes. So people began looking at the galaxies in here. We could tell the distance also from our measurements of gravitational waves. We knew that this distance was 130 megaparsecs. So they knew which galaxies were in that region. There were about 40 galaxies, so they began looking galaxies one by one, and there was this galaxy where a few days before, in the last image of that galaxy, there was nothing at this point, but on that day or on that night, it was night for telescopes to begin looking at there 11 hours after the measured merger, there was this bright spot. And this bright spot was very bright in the optical, but it also had some infrared and ultraviolet. But then the blue wavelengths became dimmer, the red wavelengths became brighter. So there was some evolution of this signal. So we had the gravitational waves and the gamma rays. Then there were no other gamma rays. These are observed times after that. There was this optical, ultraviolet and infrared, and 10 days later, there were X-rays and radio waves coming from the same spot. So this gave us a lot of information about what happened there. So the prevalent theory is that we have these 2 neutron stars that were orbiting around each other, and when they coalesced, they produced this burst of gamma rays. And this was a short gamma ray. Short gamma rays had thought to be produced by binary neutron stars coalescing, but nobody had proof until now. The gamma ray burst was not very bright, but that's because we were seeing it from the side. We were not directly in the path of that gamma ray, but close enough so it could be detected by 2 different satellites, by Fermi and Integral, both X-ray satellites. And then from the merger, there was an isotropic light that produced this optical evolution, and then there was a shock wave that produced the X-rays and the radio waves. And all of this also gives us a lot of information about the origin of heavy elements. As you may know, The elements up to about iron are produced in stars, and we are all made of those elements. We are stardust, as Carl Sagan used to say, but the bottom half of the periodic table is not produced in stars, at least not in the quantity that is observed. Those elements are produced in much, much more violent explosions, in supernova explosions, but those are not enough to explain the abundance. So the other candidate was binary neutron stars coalescing, but nobody had seen two neutron stars coalescing until now. So this was like discovering gold, literally. We can also do nuclear physics with this, because even though we have not as much detail in the coalescence that happens at kilohertz, so our sensitivity is not the best. We have the best sensitivity in the 100 hertz frequencies, but from that coalescence signal, we can constrain the ratio of the radius to mass, the compactness of these neutron stars. These neutron stars are the most compact of all stars, but we don't know how compact, and there are different theories that propose different equations of state, the equation of state of the matter inside a neutron star. And these are different models for those equation of state. And what we do is, in a plot that has this tidal deformability parameter for the first star and the second star, we have constraints. We know that with 90% confidence, those parameters are in this region. So that means that these models are not quite right. We can do this analysis under two different hypotheses for spin, but let me not take a lot of time on this. So this is doing nuclear physics. These are energies that we cannot achieve in laboratories here on Earth. We do it in stars. We can also do cosmology, because if we know the galaxy where these neutron stars are, we know the redshift. We, with gravitational waves, we measure redshifted waves. The gravitational waves have traveled over through an expanding horizon, so they reach to us with a bit lower frequency than they were emitted because of that expansion. But we don't know about the expansion of the universe in that distance. So we know the redshifted distance. But if we know the galaxy, the light from the galaxy tells us about the redshift. So we put the two things together, and now we can tell the rate of expansion of the universe, the Hubble constant. And you might have heard that Hubble constant, in the beginning, there were lots and lots of controversies about two different measurements. Then it was clear that it was around 70 per h naught is measured in kilometers per second per megaparsec. So it was around 70, and that was a measurement. Those were measurements done with supernovas and with a cosmic microwave background. Of course, supernovas are closer to us in the history of the universe than the cosmic microwave background. But these measurements, being more and more precise with time, have begun to diverge. So they seem to be different at more than a 3 sigma level. So here's a new measurement. Unfortunately, we have far from a good precision. This is our 90% confidence level. So at the 90% confidence, we can say it's between 60 and 110. Far from us to distinguish between these two very precise measurements. But we will do this in time with more statistics. And then this could tell us more about the history of the universe, whether these two measurements are different because when they happened in the universe or because of other systematic effects. So we can do nuclear physics, we can do cosmology, and we can do fundamental physics. These are the gamma ray signals, actually from the energy X-rays, And this is the time that we measure of the coalescence. Of course, the gamma rays are produced after the coalescence. Some people were surprised about how short this is, 1.7 seconds. But the point is that we have to compare these 2 seconds with 130 million years that these electromagnetic waves and gravitational waves are have taken to travel to Earth. So 2 seconds in 130 million years is a measurement of 10 to the minus 16. That's the precision with which we can tell gravitational waves travel at the speed of light. Another prediction of Einstein's theory. Okay, but we have more. We took a break after O2. We began taking data in April of 2019. We were going to take data until end of April 2020. We had to stop because of COVID at the end of March. But we took data for almost a year with a break in the middle. We call that the third observing run. And during all of the third observing run, we have the 2 LIGO detectors and the Virgo detector. We were hoping to have the Cagra detector at the end, like we had Virgo in O2, but we didn't get that chance because of COVID. So, and you can tell in here that the sensitivity was even better than we had before, especially for Virgo. So we had more detections. We had before collected 10 binary black holes and 1 neutron star. In here, what we also did is produce public alerts. Public alerts with candidates that we thought were good candidates. Well, not we, the computer algorithms saw that they were good candidates with a very low false alarm rate. We had to retract several of those, but in the end, we had 56 public alerts, 56 compared to 10 that we had before. And those public alerts also told whether what we had were binary black holes or binary neutron stars or neutron stars and black holes. And it turns out that between 3 and 5 solar masses, we don't quite know whether to call that a neutron star or a large neutron stars or a small black hole. And we have detected signals, or we have produced candidates in all of these regions. We call this the mass gap. Another visualization of this is given by this. This is information we have about neutron stars and black holes, stellar mass black holes, from regular electromagnetic astronomy. We have signals from neutron stars when they are pulsars from radio astronomy. And from those signals, the masses can be calculated, and you can see that they are mostly between 1 and 2 solar masses. There are two or three outliers, but they are mostly around a median of 1.4 solar masses. So that's a typical neutron star. 2 solar masses are quite a big solar neutron star. Nothing is known more than that. These are the electromagnetic black holes that are seen with X-ray astronomy when there is a black hole that does not emit light, but there is another star, a regular star in a binary system, and then the black hole is accreting mass, accreting particles from the other star, and these particles are moving very, very fast. Remember, this is a spinning black hole, so these particles are moving very, very fast and emitting X-rays. So from that X-ray emission, we can also tell the masses of the black holes, and these question marks are not confirmed as black holes. They don't know whether these are black holes or small or large regular stars. But here they are the masses. They are mostly between 5 and 20 solar masses. So in our first observing run and second observing run, we saw these are our 10 coalescences of black holes. So you have to look at the single black holes to compare with this stellar mass. And you can see that some were normal, if you want, X-ray black holes. But then most of the others, including The first one is much higher mass. So is this a different population of black holes? We don't know yet, but now we are doing astronomy. The neutron stars that we that coalesce, that we discovered in that coalescence, were regular neutron stars, regular masses, but when they merged, they produced an object in this mass gap. Was this the most massive neutron star or the least massive black hole? We can't tell. We can't distinguish yet until we have a lot more precision of what is that last object. And this is what we had from that third observing run. A lot more black holes, but also another merger of neutron stars. This was another merger of neutron stars producing a larger final mass in here. So we have another neutron star merger. We have two now. That is this one and this one. This one did not produce, or we could not see electromagnetic counterparts because the localization, the signal was weaker, the system was farther away, so the signal was weaker. We couldn't get enough details to localize it well, and nobody found counterparts. But we also saw several other interesting things. That's a binary neutron star. We also saw a neutron star, a mass gap object. We don't know whether this is a heavy neutron star or whether it's a small black hole. The companion was a big black hole, 20 solar masses. So this object and this mass gap object coalesce to form another big black hole. But again, we cannot tell what this object is. This is a mass gap, and now we are filling it with objects that result from the coalescence of neutron stars or one of the objects in the binary systems. We are doing astronomy. We also saw the heaviest. Notice that before we used to have a scale that ended at about 40 solar masses. Now we had to expand. This is a logarithmic scale to 160 solar masses for this heaviest system. That the two black holes in here were 66 and 85 solar masses. This 85 solar mass is more or less of the masses, or at the end of the masses of the merger objects, the final merger objects, but it's much heavier than any of the initial black holes. In fact, there are some theories of supernova explosions that say you cannot produce a black hole that heavy. So either those theories need more improvement, or maybe this 85 solar mass black hole was a product of another coalescence. But that has an impact in the number of coalescences that are happening in the universe. So either way, it's a mystery. And this is what I like about science, that you get answers to questions that you pose, but every answer brings more questions. We also had the smallest black hole masses, the smallest that we can call black hole, because this is a 5 solar mass, so we are also increasing the numbers in here. We are doing a lot of astronomy. Now we're running out of time, so I'll leave this for questions. We also have some intriguing measurements of the spins of the black holes before they coalesce. They are not aligned with the bottom line is they are not aligned with the angular momentum of the orbit, which is what I and many others would have expected. But some at least seem to have a precession spin, a component of the spin that is on the orbit, on the plane of the orbit, at least for some of these, and that makes the orbit precess. Again, these are measurements that I can explain later if somebody is interested. Let me just get to the future, because We are looking for many different sources, not just coalescing binary system. In fact, we think that when our sensitivity improves to what we want to be, then we will begin to see an astrophysical background of coalescing binary system that we cannot resolve one from another. That would be like a gravitational wave noise, if you want. We are looking for sine waves that would be producing by rotating neutron stars in our galaxy that may or may not be pulsars. So these may be new points to look for neutron stars. And we're looking for bursts that are not that do not follow the model of a sine wave or a coalescing binary system. And these could be produced, for example, by supernovas or cosmic strings or the unknown. That would be the most exciting source. This is what the next few years are going to look like. We are now we are making improvements to the sensitivity of the detectors with CAGRA 2. This is where CAGRA was hoping to be. This is where CAGRA wants to be. This we were planning to start late this year. We're probably not going to start this fourth observing run until mid-2022, next year, but we will be taking data again with better sensitivity, seeing more signals, maybe seeing unknown signals. And then, so that would take us to this 170, maybe better than 170 megaparsecs that I showed you was goal in the beginning. We have received funding to install an upgraded version that we are calling A+. This is advanced. We are calling this A+. It's not a new facility, but it is improved technologies. And with that, we could get, in many years, that's a target, not the promised sensitivity, but by the middle of the decade, we would be better than 200 megaparsecs. So we are going far, but we are doing more than that. We are actually thinking about longer, different detectors. This is the noise spectral density I showed you we had for the O3. Well, I didn't show you this, but this is what the noise spectral density we had in O3. This is our goal for A+ now, not for advanced LIGO. This is a 330 megaparsecs. This Voyager is what we could do in the current facilities if we go cryogenic, if we go to different wavelengths for the laser. If we put all bells and whistles in the current facilities, we could get to this. But if we want to go farther away, which we do, we need new facilities. And there are two concepts, Cosmic Explorer in the US and Einstein Telescope in Europe, that would get much, much farther. And to show you how much farther, let me show you in this plot. This shows new populations of neutron stars. These are populations of black holes. And this is the redshift. So with Cosmic Explorer, and there's a first version and an initial version and an advanced version, we would see most of the neutron stars. We will see all of the black holes in the universe, all of the black holes. We could tell whether there were primordial black holes. We could tell whether the initial black holes were different than the later black holes. We will do history, cosmology with this. This is what we want to be. I think I mentioned, but I'll do it again. The Cosmic Explorer concept has 40 kilometers length over the ground. The Einstein Telescope concept in Europe is underground, 10 kilometers and triangular in length. Both would be cryogenic. So lots of concepts. Of course, these would take about 10 years to get started from the time they get funded. So it takes patience. And all of these detectors that I was talking about are the ground-based detectors. If you want to detect larger black holes, coalescences and signals from larger black holes, then you have to go to space. And there's a project called LISA that would fly 3 satellites, 1 million or 5 million kilometers away, again in a triangular concept. If you want to go even farther away in time and larger in mass, you look for a galactic interferometer. You use the radio signals from pulsars as if they were the lasers from an interferometer. And then from the correlations of those, you can look for gravitational waves. This pulsar timing project in North America called Nanograv has had very intriguing results. They don't seem to be gravitational waves, at least as predicted by Einstein, but there seems to be some correlation. And if you want to go to the early universe, well, the predictions are too small to be measured with any of these detectors, maybe with pulsar timing, but those early gravitational waves would have had an impact on the polarization of the cosmic microwave background. And those are experiments that are being done now. So all of this is happening, and it's happening in these decades. So we are living in a very, very exciting time. And this is all I wanted to tell you. The era of gravitational wave astronomy is really here.
Yeah, thank you, madam, for your wonderful presentation. It was a great lecture. So I think our students have learned a lot of things about this gravitational wave and astronomy. So we have got
You
few
give me
questions.
just 1 second. I'll turn on the light. There
Yeah,
is
yeah.
a storm here.
Okay, sorry.
It's
So
not getting, it was getting dark, but it's because of a storm, not because of
uh,
light.
okay. So I can start the discussion session if you allow. So the
Please.
first question: will gravitational wave help us to improve our understanding of nucleosynthesis?
Of nucleosynthesis of heavy elements. Yes, the origin of the heavy elements, not the early nucleosynthesis,
Okay,
of, but
heavy element.
but of the heavy elements. Yes. It will give us details, especially when we get more details about the equation of state of neutron stars. That will give us more details about the production of heavy elements or R processes, which are the processes that create those elements in stars.
Okay, that means the nucleosynthesis after the supernova explosion. Yeah. Okay, so we have got another question. So, how can we differentiate the signal? We got signal from neutron star and binary star. So, how can we differentiate them?
Well, when the black holes and the neutron stars are farther away, all the approximations look the same because you can almost you can use the approximations for these being point objects. But as they get closer together, you expect tidal deformation of neutron stars, which is different than the horizon deformations that you can calculate for black holes. Now, the problem is that at those merger frequencies for the black holes, it's very short signal, and for the neutron stars it happens at the frequency where we don't have great sensitivity. But as we improve the sensitivity of the detectors, especially with the third generation detectors, we would be able to get those details.
Okay, madam. So, thanks. We have another question. So, how long ago did the gravitational wave start from its origin, which was the black hole's fusion?
Well, we are not talking about very far redshifts yet. If I can show one slide again. In this slide, you might see that with A plus, we can see a redshift that is still in the fractions for neutron stars. And with A plus, we can see a redshift of 2. And this is when we get the sensitivity of A plus. So we are not seeing far in the past of the universe. We will be able to see that with third generation detectors.
Okay, so thank you, madam. So, we have another question. So, what is the neutron star merger?
What is a neutron star merger? What is the result of that? Well, in principle, the most natural assumption is that it is a black hole. And then we will know the mass of that black hole. But there are other possibilities. And again, because we don't have enough sensitivity to see what happens afterwards, if it is a black hole, then we should be able to see the ring down of the black hole. If it is a strange object like a super heavy neutron star that survives for a while before being a black hole, or a quark star or something different, we would be able to tell if we have enough sensitivity to see what happens after the merger. And again, we'll be able to do that with third generation. We might be able to do that if there are events that are close enough to us to have a very high signal to noise ratio, but we haven't been able to do that yet.
Okay, madam, thank you. This may be the last question. I think you have already explained it. So, what is the kilonova rainbow?
What is what, sorry?
Kilonova rainbow.
Oh, the kilonova rainbow. That's what a kilonova is, the name given to these gamma ray bursts that are accompanied, that are seen together with other optical signals. And those were thought to come from, it wasn't a supernova because it wasn't as bright. So let me go back to that slide. Let me see this slide. So in here, we call gamma ray bursts when we see them up front, and then we know that they are very well defined in the gamma rays, which these were not. We know about a supernova because a supernova has a well-identified optical spectrum, and there are lots of those that have been seen, and those have been seen in coincidence with some long gamma ray bursts that last longer than 2 seconds. Now, there had been before a couple of instances in which short gamma ray bursts, shorter than 2 seconds, had been seen with some optical signals, but not as bright as supernovas. So they call these kilonovas, and they were suspected to be merger of neutron stars. And that the gamma ray burst and the optical spectrum without the gravitational waves is what people call the kilonova. I called it the rainbow because here we could see all the different wavelengths, including the gravitational waves.
Yeah, thank you, madam, for your wonderful presentation and discussion session. It was a very great webinar, and I think in near future many more interesting things will come from your LIGO and your research. So thanks for accepting our invitation, and thanks for sharing your knowledge with us. It's a great opportunity for our student and us to learn a lot of things from you, madam, and we are very grateful to you for
Thank
this
you.
program. Yeah. Bye for today, madam, and hopefully in near future we'll arrange another webinar with you if you have time.
There will be a lot more things coming up.
Yeah. Thanks, madam. Bye for today.
Thank you.
Bye.